Now, before we start off, uh, well, I pass this over to our speaker for today. We have covered six main objectives, uh, part one through part five. Uh, we went into for the part one series, we actually focused on the general basics for performance-based design, also including the details for the CSA S619 codes and how the recommendations and the parameters are included with this. And then for part two, we started to go into more understanding the concepts for nonlinear and soil spring definitions, along with understanding the processes uh, we built upon in part one from response spectrum, utilizing techniques to complete the plastic hinges, the concrete strains, as well as going to the pushover for the portal piers and how to these for better performance. Now, part three will be focusing on time history, but to be exact, we'll be conducting on nonlinear time history analysis. So the presenter for today is Prathamesh Vane, who has been presenting for the series. He is one of our technical experts within MIDAS, covering the topics and as well as general support and customer success. He has a master's in seismic analysis and design. So without further ado, I will introduce Prathamesh Vane to begin the presentation, three of the series. Prathamesh?
Thank you so much, Beda. So, okay. So I welcome you all again for the part three of this particular series on performance-based design. So, in this series up till now, we have covered the iterative response spectrum analysis to consider the secant stiffness calculations for the soil springs. Then we have also understood the nonlinear behavior in the structural elements, the basic concepts of it, and how do we compute the M5 curves and the plastic hinge properties for the substructure elements. We also found the method to compute the strain limits in MIDAS civil, which are given in CSS 619 to evaluate the performance of the structure under the pushover analysis. So today we are going to focus our attention on the nonlinear time history analysis part uh, within the performance-based design. So these are the contents of today's presentation. So firstly, we will discuss about the selection of time history records and what are the recommendations given in CSA S619 to compute these records. Secondly, we'll go into the nonlinear modeling in MIDAS Civil. We'll see how the hysteretic models can be assigned in MIDAS. We will go through one of the verification example that I have set up for one of the hysteretic model. We will learn about the fiber modeling for the nonlinear time history analysis and how to compute the strains in the fiber hinge to assess the performance of the structure. Then we will also look on to a global model for the nonlinear time history analysis of a complete bridge in this section. So let us begin with the contents of the presentation. So firstly, the selection of time history records and CSA 6 recommendations. So before starting with the nonlinear time history analysis, the question is, why do we require the nonlinear time history analysis even if we are having a detailed analysis such as a pushover analysis? So the reason that we need to go for the nonlinear time history analysis is because the pushover analysis is one of the approximate ways to compute the nonlinear behavior of a structure. As actually the system is dynamic in nature, we have represented it in terms of a static system in case of a pusher analysis to assess its performance approximately. So it does not account for many of the parameters such as the accumulation of the damage. As you know, earthquake is having an impulse, you can say a impulse at each second, and the forces are accumulating so as the damage in the structure. This type of representation is not possible in case of pushover analysis. Also, the pusher analysis is basically a single mode analysis, we could say. We saw that the loading curve or the loading pattern that we have in case of a pusher analysis is basically with respect to uniform acceleration, or it is based on the first mode or the fundamental mode of the structure. And hence, it is only considering a single mode as a representation of the structural system. However, we know that as a whole structure is multimodal in nature, it is required to consider all the modes, all the relevant modes of the structure in the analysis, which the pusher analysis could not be considered. Moreover, pusher analysis is valid mostly for the regular type of bridges, wherein the first mode or the fundamental mode is governing the with highest amount of mass participation, which is generally over 70-75% of the mass participation. In such a structure, push-or analysis could be considered as valid. However, some complex bridges, complex structures wherein there is coupling of modes, then in that case, the pushover analysis is not completely valid, or it is not recommended to use the pushover analysis. And hence, there is this need of nonlinear time history analysis or nonlinear dynamic analysis, so to say. Thus, how does the nonlinear analysis in this case works is it solves the equation of motion at each steps and records the response of the parameters. Now, the equation of motion that we know is mu double dot plus ku plus cu dot is equal to minus m ug, where ug is basic ug double dot. So ug double dot is basically nothing but the acceleration of the ground or the seismic force that we could say. This equation is solved step by step in the processor to compute the different parameters as a response. Now, if you could see on the screen, so if this is my structure, which is modeled with a nonlinear uh, model with respect to different hinges at the locations where the plastic hinge formation is possible, and an earthquake is or the earthquake record in the form of acceleration versus time is applied at the base of the structure to generate a response within the structure. Now this particular response could be in different forms. It could be in the form of acceleration versus time, it could be in the form of displacement versus time, etc. So the time history analysis is giving us this particular graph of the output. So you can see that it is varying and it is not constant. So in pusher analysis, we used to get one single value for the analysis. However, in the time history analysis, we get a record of the response of the structure with time, and generally the peak response of the displacement or the peak response of acceleration in that case could be considered as the governing characteristic for that particular time history application. Now, we should note that this peak response within the structure in terms of acceleration or the displacement could be different in case of different time history records. So there is always a certain amount of variation in the response that we are getting from the structure in case of the nonlinear time history analysis. So it is very important to adhere with the recommendations of the code to consider a certain uniformity or a surety in the analysis results. Now, the time history analysis, we can look into two different things. Firstly, we need to look into the ground shaking intensity measures to evaluate or to get the records or the time history records from the past earthquakes. And these time history records that we are getting, we are going to apply it over the structure to get the local and the global behavior. So to assess the damage within the structure or the performance of the structure at one particular level, this procedure is adopted and the entire uh, process can be termed as evaluation of the seismic performance of the structure. So first things first, we will be looking into the ground motion selections first. So we have learned about how to model a structure. Firstly, we'll look into the ground motion selections. So the ground motions for the dynamic analysis, as I discussed, that each ground motion will produce a different response of the structure, and thus it is very important to choose some correct ground motions to assess the response. So what is the advantage is basically here is it will cover the full range of the structural behavior from elastic to inelastic behavior and finally a global dynamic instability level. So what does it means is the under the ground motion the structure will be showing certain elastic range before, then after a certain damage it will move into the inelastic zone, and finally if the intensity of the record is more, it can go into the global instability as well. So there will be a record to record variability within the response of each ground motion. So it is very important to select the ground motions and to a certain parameters. It could be depending upon the intensity, that is M. It could be the range, that is R, or it could be the subsoil data. Now, the ground motions that we are getting from the past earthquakes are, it is not always true that it will be equal to the demand response spectrum or the target response spectrum in that case. So these time history records that we get from the past earthquakes are to be scaled to a certain level such that it is actually somewhere close to our target response spectrum. Now, this scaling can be done by using the scale factor. Generally, the scale factor is considered to be within the range of 2 to 4. So we should not scale the ground motions with the scale factors generally which are more than 4, because it will not actually reflect the correct behavior or the correct characteristics of that particular seismic event. So generally a scale factor range of 2 to 4 is valid, and this scaling is done in the time domain only. Now, the other method is with respect to the spectral matching, wherein we work in the frequency domain to change the characteristic of the ground motions to match our target response spectrum. Now, as I say, the target response spectrum. So the target response spectrum is nothing but the amount of seismic uh, intensity at that particular location of the bridge. So the seismic hazard at that particular location of the bridge can be calculated in the form of the response spectrum data available at the site at that particular location of the bridge. It can be in the form of an uniform hazard spectrum, or it can be also considered to be in the form of a CMS type of target spectrum. So depending upon our accuracy that we want to do the analysis with, we can choose our target spectrum. For the important structure, generally site-specific hazard assessment is done to calculate the target response spectrum at that particular location. So once we are done with the selection of the time history records, now it comes down to the modeling of our structure for the nonlinear behavior. So you can identify this figure that we had discussed before. So this is basically a fiber model of one of the plastic hinge that we can consider. So it is very important to consider a correct hysteretic model or a correct nonlinear model for that particular structure so that the assessment is accurate. And hence, generally, the calibration of these type of hysteretic models is required before assessing a particular structure. Now, this particular calibration data are available in various research papers. So depending upon the type of the section that we are having and depending upon other characteristics such as the material properties or the location of the structure, etc. On that basis, we can choose one of the hysteretic model for the assessment. So there are different types of hysteretic models which are available. Sometimes we also consider the lumped type of hysteretic models. We will see in the further presentation what are the different types of lumped uh, hysteretic models available in MIDAS Civil. Similarly, there is a fiber hinge type of a model wherein we divide the entire section into certain fibers and uh, give a certain characteristics uh, to each fiber to assess the nonlinear behavior of the structure. So, as I said, the nonlinear hysteretic modeling can be done within in the two forms. So it can be in the form of a moment rotation or a fiber hinge. Whatever type of the material that we are dealing with, it is very important to do the calibration of the structure or the fiber hinge that we are doing. So you could see that for this particular assessment, um, the black color curve is basically the experimental results that were taken out from one of the tests which were done in the laboratory. And the red color curve is basically the analytical curve which was obtained from one of the software programs. So this particular hysteretic curve which was generated for the model, the hysteretic model which was considered, shows a good resemblance between the analytical and the experimental results. And such type of calibration data is required to confirm the hysteretic models that we are choosing. So coming to the source of ground motion, so there are different types of uh, real-time records which are available for assessing the performance of the structure under the seismic event. So the advantages of the using the realistic ground motion record is that we are getting an actual simulation of an earthquake event under the amplitude, frequency contained, duration of the shaking, and the different number of cycles for the shaking remains same for the bridge that we are testing on. So it is very important to choose a realistic ground motion and which conforms with the characteristics of the location of the structure. So we shall also consider the source of the event, where the seismic event is happening, what type of fault it is generating, and we shall also check what is the path it follows and at the site location, what is the soil type which is generated. So generally, we will choose real-time records which are confirming with the characteristics of the location of our structure depending upon the source, path, and the site condition. The real records are having certain disadvantages also, or rather than saying disadvantages, it is more sort of a limitation. So we will not always get certain ground motions which are confirming very accurately or to a good level with our characteristics of the structure location. So there is always a lack of ground motions record from the past earthquake events that we see. So not all combinations of the intensity M, the distance from source to site D, and the soil characteristics are available. Thus, it is difficult to get a certain records, and then in that case, what we do is we use synthesized records, or depending upon the uh, uh, records that we are having, what we do is we do certain syntheses on it. We generate an accelerographs, um, which are called as an artificial accelerographs, and do the analysis using those records. So it is very important to also be aware of the near surface geology before assessing or confirming the seismic records for the analysis. So the impact of soil conditions on the ground motion characteristics is considerable. So just to demonstrate that, if you could see that this is one of the graph which is taken out from the Kramer's book. So you could see that the amplification factor for the soil or the site B, which is having the soft soil, and the soil type A, which is a rock type of soil, you could see that the peak amplification factor is confirming at different frequencies of vibration. So we know that the soil generally vibrates in the first or the fundamental mode of analysis, fundamental mode of vibration, and for that particular mode of vibration, the soft soil is having a good amplification or a very high amplification factor at a shorter frequency, and soil type A is having somewhat at a larger frequency. So this can also be reflected in case of the response spectrum also. So the response spectrum, you could see that as the soil becomes softer, there is a certain shift in the peak response. For the rock type of soil, we can see that the peak response is actually seen at a certain lower time period. However, for the soft type of soil, we can see the peak response at a higher time period. So we shall also consider the variation of the soil. So for example, what I am considering here is one of the example from a Mexico City. So the location of the two station UNAM and SCT, can see that they are located in different soil deposit level. So foothill zone is UNM, and older lake deposit are in SCT. So even if there is a distance of an considerable kilometers, we can see that the records which are available at UNM and SCT are quite different. So these are the time history records which are available at these sites. So even if the location of the SCT was around 350-kilometer distance from the city, we saw that there are more damages in the far distant within the city. However, near the epicenter, the damage level which was observed was very moderate one. So this was due to the soil amplification, we could say. So you can also see from the graph of the response spectrum that the peak ground acceleration for SCT is larger than the UNAM station. So we shall consider these characteristics such as the distance from the location of the epicenter or the fault plane, and the uh, intensity of the earthquake, and also the soil characteristics before considering the record selection for the time history analysis. The next process is the scaling of the ground motion records. So the scaling of the ground motion records, we first take the original time history. This original time history can be taken from different sources. One of the source which is quite famous and generally used is the peer NGA West 2 website, wherein we can easily get a time history records from numerous events which occurred in the past. So we can select the ground motion depending upon M, R, and the soil data. Now we generate the response spectrum for that particular original time history record, and we try to check the response spectrum whether it is confirming uh, to the target response spectrum or not. So what we do is we apply a scale factor such that SA from the target response spectrum divided by SA from the original response spectrum of the time history, and we multiply that scale factor with the original time history record to match the um, target response spectrum. And this time history which is generated, it is a scaled time history record, and these scaled time history records are now applied to the bridge structure to assess its performance. Now, there are two types of scaling that generally are seen for the ground motion records. One is the scaling with respect to the application of the scale factor, and second is the spectral matching. So you can see that for the blue color curve is basically my target response spectrum, and the red color curve is one of the time history records response spectrum. And for the fundamental time period of the structure, that is T1, the time history record is scaled to the target response spectrum such that the spectral acceleration for the target response spectrum and the records are the same. So this type of scaling is done at one point. However, if you see in the picture below, if we scale this record to the target response spectrum, we can see that at the fundamental time period location, there is an exact match of the spectral acceleration. However, at other time period location, the match is not quite great. So in that case, the complete structural behavior under the target response and for that particular time history would not be valid. So in that case, what we do is we scale the particular response spectrum within a range of motion. So if this is our multi-degree of freedom system, we know that there are different modes of vibration, and these modes of vibration, so T1 will be basically my fundamental mode of vibration. So this is basically my T1. Now we know that in case of the multi-degree of freedom system, different mode will have different influence on the structure, and depending upon the mass participation, they will influence the structural behavior. So it is very important to consider these modes to match the target response spectrum as well. So what we do is we consider a range of uh, period over which the matching of the matching to the target response spectrum is done. So the to the left side of the fundamental mode, we match it up to the higher modes of vibration, and on the right side, wherein the T effective is considered, we match up till that point. So in this case, T effective is nothing but the increased time period of that particular structure. And how the time period increases basically, once the structure is undergoing the time history analysis, it will undergo certain uh, uh, damage, and due to that particular damage, there will be increase in the time period. Due to that particular increase in the time period, the fundamental or the response of that particular to the vibration will change, and thus its characteristic would also change. And hence, we also need to consider the increased time period to compute our target response spectrum. So that is the reason we consider an entire range of matching for our target response spectrum. So once that is done, the it is under the scaling. Now, if you want to match our target response spectrum, then there is another method which is called as the spectral matching. In case of spectral matching, different criterias or formulas are considered by which our uh, target response spectrum and the seismic record response spectrum are completely matched to the uh, with each other. But we need to be very careful when using the spectral matching method, because it changes the actual characteristics of the structure. It changes the actual characteristics of the ground motion entirely, because it is working in the frequency domain, and it is changing the frequency response of the entire structure altogether. Hence, this spectral matching technique shall be used very, very carefully. So the CSS 619 says that the spectral matching or scaling has to be done to generate the ground motion records up to the target response spectrum, and these records shall not fall below 90% value of the target response spectrum within the period range. So if the period range is basically specified from point 2 T1 to 2 T1, where T1 is basically my fundamental time period, and under this particular range, my target response spectrum or my scaled spectrum shall not fall below 90% of the target response spectrum, which is this. So we need to be sure that each record is over the 90% of the target response spectrum. Next, the number of ground motion records, as we discussed, shall not fall below 10%, where the range consider for this is TR, which is for which the upper bound is basically the greater of 2 times of the fundamental time period and 1.6 seconds. So greater of this is to be considered as the upper bound. The lower bound is basically the at which 90% of the mass participation is occurring in each orthogonal direction, and zero point 0.2 times of the t fundamental time period. And the lesser of this is basically considered as our lower bound. So this is the matching range that we need to consider. Next, the ground motion load cases. There are two processes. The firstly, the number of ground motion required are greater than 11. That is the minimum number of ground motions which are required to ascertain the response of the structure. So that is called as a suit of ground motion. So for each suit, the horizontal motions, there can be two scale factors for each ground motion component. So there are two ground motion component in each horizontal direction, and there can be two scale factors which are used for scaling. And the vertical motion in this case shall be scaled up by the larger of these two scale factors. That is the process one which is recommended. However, the second procedure is we can also use a single factor for scaling of both the ground motion records. But that single factor is basically computed by taking the geometric mean of the two components. of the earthquake. So firstly, we'll take the geometric mean of the two components, and then we will scale our time history record by using a single scale factor to match the target spectrum in the range. And then this same factor is to be used for the vertical motion. So any of the two processes can be used for the uh, scaling and matching of this ground motion with the target response spectrum. Okay, so with this background, now let us go on to the nonlinear modeling in MIDAS Civil. So in case of a nonlinear modeling, there are, as we discussed, there are two types of hysteretic models which are possible. So first is the lumped type. The lump type of hysteretic model will be consisting of two subtypes again. We can either define them as the moment rotation curve, or we can also define them as moment curvature distributed type of model. Now these model, which is the moment curvature distributed, we also saw in case of the Pushore analysis. The only difference in this case is the moment curvature curve will remain the same. The only thing which will be added is basically the uh, response of this particular model to the reversal in the cycle. So the degradation of the stiffness in this case, all these parameters shall be mentioned additionally with the moment curvature distributed model that we saw in case of the Pushore analysis. Then we are having the fiber hinge type of a model in which we can specify the data for each hinge separately and check the results. So this is far more accurate in terms of the analysis. Uh, uh, However, it will take more time than the lumped type of hysteretic model, which is a bit more approximate. So if you consider the lump type of hysteretic model, we are having a various hysteretic models. So depending upon the type of hysteretic model that you need to choose, which can be referred from the research papers, depending upon the calibration of the data that we discussed earlier, you can choose various type of hysteretic model from the list. So in case of the moment rotation and as well as the moment curvature distributed, there are different types of hysteretic models such as the kinematic hardening, the Clough and Benson, Takeda model, and slip models are available, and also the multilinear elastic plastic models are also available. So we will be focusing on few of these model in our discussion here. Secondly, the fiber hinge modeling can be done by specifying the inelastic material properties for the confined, unconfined, as well as the rebar data. So we can cut the fibers within the section and assign this fiber divisions as a plastic hinge in the time history analysis. Along with that, there are nonlinear models with respect to some special uh, devices. So if we are using the dampers in our system, then in that case, the viscoelastic dampers, the steel dampers, the base isolators are available. Along with the base isolators are about lead rubber bearing type, or the friction pendulum system, or the triple friction pendulum system devices are available within the program for the assessment. So we will not touch on these devices today. We will restrict our discussion to the uh, nonlinear modeling with respect to the plastic hinges only. Now let us go out to one of the verification example that we have here. So this is one of the bridge pier that we are having. It is basically a tapered hollow concrete pier with the outer diameter of 6.5 and the inner diameter of 4.5 meter and a height of around 40 meters. So this is basically a railway bridge pier that we had, and the assessment of the railway bridges for seismic analysis was conducted on this bridge pier. So for this particular structure, what we are doing is we are using a multilinear plastic pivot type of model for the plastic hinge definitions. And the types of loads that we are going to apply for the verification are these three. Firstly, it is incremental static load, which is nothing but like our pushover load that we could say. Secondly, there is a quasi-static cyclic loading. So this type of loading, you could see that it is uniformly increasing after 2 cycles each, and this type of loading is generally seen in case of laboratory testing. And finally, there is this seismic time history record that we are having, which is an earthquake record for one of the past earthquake events, which is used for the assessment of this particular model. So let us move on to MIDAS Civil now. So as we discussed, this is the bridge pier that we were talking about. So let me just activate the loads in this case first. So if I go to, first I'll activate all the boundaries and all the loads which are applied. So I'll just display these loads. So you could see that the loads that I'm considering here is the sulfate and the nodal load at the top. So this nodal load is basically a superstructure load that we are having, and this particular superstructure load is from the superstructure from either side of this particular bridge. Now the loads which are applied on this particular structure, as we discussed, there are four time history cases that you could see. The initial dead load plus live load, that is my initial case that I'm considering. Then there is this push load, a quasi load, and a time history load. So if you see the time history load that we have defined, so this is a time history record which is having a 55 second of total duration. The time increment that I'm considering here is 0.001, and it is ordered in a sequential loading. So what does it mean is the NDL plus ballast loading, that is my sulfate of my structure, plus the load from the superstructure, that is this load case which I'm having, is basically already present on that particular bridge, and then the bridge is loaded for the seismic record. The method of damping that I'm considering here is the modal type of damping with uh, 0.05 damping ratio. So this is the load case that we saw. Then there are different time history function. The time history load case that I'm considering here is basically an El Centro earthquake of 1940, and both the direction of this El Centro earthquake are considered, and a ground acceleration load case is defined. So if you want to verify the results for this particular bridge, I'll move on to the time history results smart graphs that we have in MIDAS Civil. So, so this is basically the result of the push case, or the inelastic pushover analysis case that we uh, did on this particular structure, and applied a load on the top of the structure, and adhering to the uh, models that we are having, the results can be seen. So second, so this is the hysteretic curve which is generated for my quasi-permanent type of loading that I'm having. So this curve, you can see that it is adhering with my plastic pivot type of the hysteretic model which I have given for this particular structure. Then finally, I applied a time history load of the Sunda earthquake, and the results for the moment curvature at the plastic hinge location are something like this. Now, if I superimpose all the three load cases together, so you could see that the red color curve and the green color curve are basically overlapping. So it means that the model or the plastic pivot model that we have considered for the nonlinear record is adhering with the static pushover case for which the moment curvature curve was specified. Also, the blue color curve in here is basically nothing but the time history results that we got for this particular structure. And the loading and the unloading curve for this particular time history records are well within the inelastic moment curvature curve that we have specified for this model. So this is one of the verification that we did. So also, if I had to show the pushover the plastic hinge that we have considered for this particular structure, so I'll just go to the inelastic hinge properties. So this is the pier hinge that we have defined. It is having moment curvature or M phi distributed type of a relationship, and the multilinear plastic pivot type of model was used. So how do we get the force deformation or the moment curvature diagram for this? This particular a table of moment curvature is basically been taken from the general section designer in MIDAS Civil that we saw in our previous seminar. So this curve is used, and then we have assigned certain hysteretic parameters to consider the unloading and reloading of the structure. So this particular parameters are basically been considered from one of the research papers that we had. So in this way, we can define the plastic hinge, sorry, inelastic plastic hinge in case of the time history analysis, adopting the moment curvature relationships. So coming back to our presentation, now let us discuss one of the fiber hinge models that we have considered. So this is one of the structure that we had. So there is this portal pier in this particular structure. It is basically a four span uh, a PSC composite type of a bridge, which is having seven girders on the top. And we have considered an portal pier system from this bridge and isolated it to carry out the seismic analysis on this particular portal frame. Now, for this particular portal frame, the details are as follows. The height of the pier is around 15 meters and the center to center distance between both the piers is 9.2 meters. Number of bearing on the pier cap is 14, and depending upon those number of bearings, we have applied the static load on these bearings to check to apply the loads from the superstructure. The pier diameter is 2 meters. Grades and concrete and steel are given. The bar size for the longitudinal as well as the shear reinforcements are being shown here within the details. So for this particular section of my column, we have generated a fiber model in MIDAS. So I'll just open that particular structure. So if you want to generate a certain fiber model, in this case, you can see that an elastic hinge properties are assigned as a fiber hinge model. So I'll just go to properties, and if I want to see the properties, so we have given an auto calculation for the M5 characteristics for this particular structure, and the fiber model is been given here. So if I just click on the three dots, you can see that the fiber model for this particular structure is section is shown here. The yellow color data is with respect to the confined concrete. The blue color fibers are with respect to my unconfined concrete, and the pink color circles are basically my rebar data that I'm having. So each fiber with respect to confined and unconfined concrete are defined with respect to the Mandaris model, and my steel is represented with respect to the Park strain hardening model. Now, the details with respect to the Manders model and the Park model were shared earlier in our seminar series. However, I'll be also sharing a step-by-step tutorial guide to model the entire fiber hinge to for this particular portal frame system at year end. So let us first check the results that we got. So the advantage of using a fiber hinge model is we can compute the strains directly from this particular fiber hinge models. So you know that it is difficult to compute the strains for the performance based design objectives or different performance levels when we are using a lumped type of plastic model. So, but in case of a fiber hinge modeling, we can compute the strains within the fibers directly without undergoing any type of calculations. So to assess those type of results, so what we can do is we can see the results for each fiber. But before that, for this particular record, the time history record of one of the earthquake event, the moment curvature relationship that we are getting, or the moment curvature data which I am getting for one of the plastic hinge at the bottom of this pier system is something like this. But I am more interested in the result from the fiber hinge model. So what I'll do is I'll go to the results and time history analysis. We'll go to the fiber section and click on the estimate yield strength for fiber section. So we can select any of the location of the fiber section that we are having. So we can select the different load cases as well. So I'll just select the load case, which is my TH. Then we can see the results in terms of SN and SS. So SN is basically my strain, and SS is nothing but my stress. So for the time history record that I'm having, I can assess the strain in each fiber. So let us say we can select the position of 1, 2, and 3 depending upon the distribution of the section that we have done, and then we can select our fibers from the display. So let us say I select this particular rebar, and if I want to plot the graph of this particular rebar data, I can get the graph for the time history analysis at this particular point. Now this particular graph is basically nothing but the stress strain relationships. Now I can copy this particular data in the Excel sheets and check whether my strain is basically overshooting my performance objective or not. If it is overshooting my performance objective, then in that case I need to redesign my structure. So this is more simpler method. However, we need to note that the amount of data which is generated in this case is very high, and that is the reason it is not much popular. So you can see the strains in each rebar here. And similarly, if you want to see the strain in within the concrete as well, you can select the concrete fiber and evaluate the strains which are generated in each fiber. So this is one of the uh, uh, other modeling techniques that we are having in case of nonlinear time history analysis. Now, we are actually running short of time, but I'm also having one of the complete global bridge model for the nonlinear time history analysis. It is a four-span PSC composite bridge with the fiber modeling done at the base. So it is similar to the one that we saw earlier. However, the entire structure is considered for the global analysis in this case. So we can see the similar type of results in this type of modeling as well. So I'll not drop into that, but I'll share the model with you so that you can verify the results that are generated in case of these type of structures. So coming to the conclusion from the entire webinar series. So we looked at the principles of the performance-based design, and we saw the nonlinear aspects to consider the performance-based design. Then we also saw different methodologies and gained insight for the PBD and the iterative response spectrum analysis. We saw how we can consider certain effective methodologies to utilize MIDAS Civil as a tool for seismic analysis. So this was all from my end for this particular series. I thank you all. Uh, Beda, over to you for the questions, if any, from the our viewers.
Thank you, Prathamesh. We'll get started with a few of the questions. Hopefully everyone can see the screen. Prathamesh, do you see the screen?
Yes. So coming to the first question, what is the importance of time step selection in nonlinear time history analysis? So for choosing the time step in case of the nonlinear time history analysis is basically dependent upon the sensitivity of the time step. So generally, it is a thumb rule that depending upon the time history records that we are having, we know that when we generate the time history records, these time history records are spaced at one particular time interval. So let us say that it is around 0.01. So generally, 1/10 of this particular time interval of the record is considered, that is 0.001 or 0.005. So minimum of the 1/10 of the interval or the 0.005 seconds is considered as the time step in case of nonlinear time history analysis. The second question is, how does damping influence the result of a nonlinear time history analysis? So the in case of the nonlinear time history analysis, the damping plays a very important role, and there are various methods to specify the damping to our structure. So for generally what people do is, or the engineers do is, they use the modal type of damping. However, the modal type of damping should not be used in case of nonlinear time history analysis. We generally prefer the mass and stiffness proportional damping so that we can get a range of damping for different modes of the structure, so that the entire range of the structure is covered. So you can use that. So coming to the third question, can we assign damping values for different materials in MIDAS? So the answer is yes. So basically, in structure which are having different materials coming together, such as RC plus steel, then in that case, assigning one particular damping value to the entire structure is actually incorrect. So in that case, we need to assign different damping values for different material. And in MIDAS, we are having this feature of group damping, for which by which what we can do is we can group this type of materials together, and we can specify different values to different materials for the damping. Coming to the fourth question, can you incorporate other extreme loads like blast or impact? So the blast type of loading can be addressed in MIDAS. Uh, However, a detailed analysis for this type of structure is also required. There are certain blog articles over this for blast and impact loading. So we can utilize MIDAS for this type of analysis, or we can also utilize the other tool, that is the MIDAS FEANX, to assess the blast or impact type of loading more accurately.
Okay, next page.
Coming to the fifth question, how can the parameters be optimized for yield, strain, and hysteresis loops? So this is actually a very generalized question. So for this particular question, as I discussed, the hysteretic loop parameters are generally found from the calibration data that is generated by different researchers. So this calibration data is to be used to consider the hysteretic loop parameters. The sixth question, can you go over the aging effects for degradation? So in case of degradation, the degradation can be assessed for the structure in two ways. First way is to reducing the stiffness of the section as the material is degraded, and the second way is to decrease the modulus of elasticity for that particular section. So basically what we are doing is we are trying to reduce the EI value for one particular section, so that the stiffness of the section can be reduced. So uh, for this, uh, we can use the section stiffness scale factors in MIDAS to consider this aging or degradation effect, what we say. Coming to the question 7, how is the software capturing the P delta effects for taller structures like pylons? So for this, when we are considering the taller structures, we know that the P delta effects are very important. And to consider this in the analysis, whether it be the pushover analysis or whether it be the time history analysis, we are having the options of P delta analysis within these analysis, so that if you just check on that particular checkbox, the P delta effects are considered. Similarly, for the nonlinear time history analysis, we can do the geometric nonlinearity. So for geometric nonlinearity, there is in case of geometric nonlinearity, P delta effects are inherently considered. So uh, both pushover as well as the nonlinear time history analysis can consider the second order effects here. So the eighth question is temperature effects integrated with the nonlinear material properties. So currently the temperature effects are not integrated. In case of the nonlinear material properties, we only have the material nonlinear properties in which the material stress strain curves can be specified. The temperature effects are basically only considered in case of a linear analysis, wherein the temperature coefficient is utilized by the program to consider the temperature rise, fall, or the gradient type of loading. So
Okay,
if yeah,
I think that's it. Prathamesh, thank you for the questions and answering them. And thank you for the attendees for participating in today.